through this. So what I wanted to do first is just kind of review what we learned in November, since some of you weren't able to attend in November. So really briefly, in November in course 1, we talked about the difference between regression and classification. Regression in Tableau is called trend lines. And the core difference between the two is that regression produces a continuous prediction. Price is a green pill, if you will. And that's represented by this line here, whereas classification produces a discrete prediction, a blue pill, if you will. So that's the core difference between regression and classification. And then both regression and classification comprise what's called supervised learning.
I don't think you guys are sharing your screen. Never mind, maybe you are.
Yeah, it says it's
okay.
sharing.
All right. Oh, thank goodness we are sharing. All right, so supervised learning is we're shown the answer at training time. So the basic idea is that at training time you have this extra column, at test time you don't, and at test time you try and recreate the column that you saw previously. In contrast, unsupervised learning generates a new variable de novo, often by doing fancy statistics. So this, for example, this species column is not known at training time. It's created from scratch. And an example of unsupervised learning is clustering. So in Tableau, we cluster by creating a new column, ex nihilo, and place it on the color shelf. So there's a basic distinction: regression, classification, supervised, unsupervised. All right. We also touched on the fact that you can use regression to, and you can, from there, you can create a classifier through thresholding. So the idea is logistic regression produces a probability pill, which is a continuous pill. But you can use an identity function, a threshold, at an arbitrary cutoff to generate a blue pill. So you can move from probability of species to a discrete species by this thresholding procedure. Also, what we touched on is we talked about how regression has two components. You wouldn't know this by looking at Tableau, but regression does have two components. It has a structural component. This is the thing that's visible in Tableau. It's that line. But there's also a random component, which is at each point, at each data point, we assume that the errors are distributed, follow some probability distribution. In this case, we assume that it follows a normal distribution. So if, for example, you have a very wide distribution of errors down here and a small distribution of errors up here, that's called heteroscedasticity, and that's a problem you have to accommodate for in your model. Okay, so there's two components to regression is the takeaway from this slide. Okay, and then I also wanted to talk a little bit about generalizing regression. So we talked about the two components, but there's also, and these two components are related. So y here is plugged in as the mean of the random component. So in this previous picture, the center of these yellow distributions is y, the blue line. So the core way to generalize this is you take this y here and you pass it through a function called the link function, g of y. And in a generalized linear model, this link function can be nonlinear. So let's see. So if it is linear, if gy equals y, then you recover linear regression. But if you have a sigmoid function, then your y is transformed and you create logistic regression. And more relevant to neural networks, you can pass it strange nonlinearities like this, and then your regression function is more of a ReLU-like neural network function. Okay, so before linear regression, there were two components. Now we're introducing a link function, which can be nonlinear. All right. Finally, we need to relate logistic regression to neural networks. So the core idea is that a neuron can be thought of as computing a sum of the electrical activity of its axons. So the entry point of a neuron computes the structural component of linear regression. Okay. And then the threshold function of a neuron, the firing activity of a neuron implements the link function. And then in neural networks, the random component is not directly represented. All right. We also talked about how to grade a model. So suppose we have a regression function, a trend line that looks like this. You can tell yourself that, yeah, this seems like a pretty good trend line. If I saw this in Tableau, I would accept it. And the next step is you need to take each parameter, your slope and your y-intercept, you put it in a new table, and you translate this good feeling into a number. And then and you keep doing this. Oh, and then you plot it, right? So you put slope, y-intercept on a graph, and then you say, okay, at this location, I have a pretty good model. But now you need to think about other possible answers. So this is a less good trend line. You wouldn't be super happy with it if you saw it in Tableau. You translate all of these numbers into a new row in your table, and you're starting to see, okay, so maybe I can graph that as well. You continue this process, and you start to see that this space right here, you're sampling from a space that looks like this. So if you take hundreds of samples, the entire space looks like this. So parameters around this location, parameters that have a slope of around 5, a y-intercept of about -15, these are the best. But if you have parameters -5, -35, that's a pretty bad line. So this is your total loss surface. And you can instead of putting loss on color, you can put loss on the z-axis, and you start to see a shape that looks like this. And this is called loss surface, and this is what gradient descent takes and tries to improve on, is this loss surface. So the idea is that there's a way to automate moving around in this loss surface to find the best model over here, and that's called gradient descent. So the idea is if you take an arbitrary model like this with a parameter combination that's here, you can see that it's got a fairly high loss. This is not a good model, but you can compute the slope of where you sit right here to move towards the bottom of the surface, and that's what gradient descent does. So you find the gradient of the slope, and then you move in that direction, and that's this is a visualization of gradient descent in action. You're moving in parameter space towards the bottom of the surface, and that corresponds with generating more and more accurate models. So that's a crash course of what we learned in in course 1. I guess. Yeah, okay. Okay, so are there any questions, comments before we breeze into new material? And I wow you.
Potentially stupid question.
Oh,
if you do linear regression and you compute the minimum least squares, aren't you going to get automatically the best model? You don't need to do any.
That's a very good question. So, and I didn't cover this very much, but there is a way in linear regression to find the minimum location, the best model, analytically in one step.
Yeah,
so instead of exactly. So instead of following the curve, you can kind of just jump to the minimum. That's true, but when you inject nonlinearities like logistic regression, you lose your ability to analytically solve, and you've got to resort to something like gradient descent. Okay. Any other questions, comments?